we start. So good afternoon, everyone. Welcome to this further installment of the August Mini-School on an introduction to set theory given by Professor Zurab Janelidze and Professor Amartya Goswami. Yeah, since you all been here before in the mini-school, I don't need to spend lots of time in the introduction. So Amartya and Zurab, over to you. You're welcome to start sharing the screen. And while you do that, I will remind the participants to please use the Q&A to ask questions or raise your hand, and at some stage we will give you then the right to ask the question in person. Yeah. So please, I'm not sure if Amartya or Zurab starts, but you're welcome to start as a team. Thank you very much.
Thank you very much, Francesco. Is the screen being shared? Just want to check.
Yes, we can see it. Yes, we can see it.
Okay, wonderful. Thank you.
Yeah, thank you.
So, Amartya, do you have any ideas where we go from where we left off last time? Or maybe if participants would like to make some suggestions, they should feel free to put their requests in the chat.
Yes, I think that would be more interesting if we get some suggestions from the participants, and accordingly we can discuss set theory. So maybe we can wait for 1 minute.
While we're waiting, while we're waiting, I want to say that the main point to be understood about set theory is that it is a language which allows you to formalize all of mathematics.
Yes,
so so maybe one of the first things to learn is how to actually do that, starting with some familiar mathematical ideas or phenomena, and seeing how it can actually be encoded in the language of set theory.
Right. Any suggestions from participants? Do you like to us to discuss any specific things, or discuss any specific questions or specific areas, or even specific structures? Which so far nothing, Zurab. So maybe then we can actually think about something. I was just thinking, maybe why don't we just pick up a simple mathematical structure, which is quite relevant with respect to applications in other areas, specifically in physics as well. For example, vector spaces, and just try to understand how it can be completely represented. Okay, I think we have a such question as yes.
So you're saying, Amartya, we should maybe see how we could embed the notion of a vector space in a universe of sets. So
yes.
Okay, maybe we have a very quick recap that what we described last time was that each universe of sets consists of a collection of objects which are sets, and then sets are related to each other by the element relationship. So every set could have some other sets that are elements of that set. And for example, in this picture, we have set X having exactly 3 elements, A, B, and C, and then this is written like this. If we now consider the idea of a vector space,
yes,
representing a vector space in this language means that we want to explicitly describe which of these points are vector spaces. So what does it mean for a set to be a vector space? Because in the universe of sets, everything needs to be a set. Anything we present, anything we.
So maybe first write the traditional definitions of a vector space in terms of only set of axioms, and then we try to understand each of these axioms. How can we represent it in terms of sets?
Well, before axioms, we have structure, right? We have
of course we
set
have this
B of vectors, and we have addition of vectors, and we have a 0 vector,
Right.
And then we have multiplication of scalars and vectors, of vectors by scalars, right?
Then we have the scalars.
Where scalars come from a field in general, but for simplicity's sake, let's stick with the field of real numbers. It could also be the field of complex numbers or any other field. So in a way, we maybe want to first see how we can represent real numbers in this language, but I would suggest that we actually go into that topic later on at a later stage. For now, let's suppose we already know how to represent the set of real numbers inside a universe of sets. And because it's not so difficult to think of real numbers as a set. But then this whole system of data, how does that become one single object of the universe? Maybe that will be interesting to explore.
But also maybe we also should incorporate the fact that R has itself a structure of it, so which includes some other operations similar to what we have for V.
That's true. That's indeed true. R itself has some structure over it. We have addition of real numbers. We have the real number zero.
Real numbers.
Then we have multiplication of real numbers. Then we have real number one, which is a special number compared with respect to multiplication. We could make this a bit shorter maybe and just disregard the special elements and introduce them as part of axiomatics. So disregard them from the structure, and that's also possible. But let's just work with this for now. So this entire thing is not just a set of real numbers; it's a set of real numbers with other ingredients as well. And so the question is, okay, how can we think of this entire ingredients, not just the information about the set of real numbers, but the information about all of its operations as well, which are needed for definition of vector space as a single dot here in the universe, and then the same for more complex structure of when real numbers are combined with a set of vectors and its own structure of additional multiplication. So,
sorry, Zurab, I think Partho has a question. Is it possible to have ... in A, in B, in C? It's not clear to me what's...
I think what he means is an infinite chain of...
okay, yeah.
Yeah, it depends on axiomatics. We didn't make a full list of axioms for set theory, so it would depend on axiomatics. And if I'm not mistaken, one can choose an axiom which will eliminate this possibility, but one actually doesn't want that. Yeah, so I think it's called axiom of foundation, which tells you that everything should begin from somewhere. So you can have increasing sequence of element relationships, but not decreasing one. But that's a more technical question related to the axiomatics of set theory, which we are not going into now, because, as we said, there are many different axiomatics as well. So coming back here, the first thing one might want to understand is, what are these tuples? How do we think of a tuple as a set? And maybe we can begin with something more primitive, an ordered pair of
the Cartesian product, which you know from the geometry.
Well, before we go to Cartesian product, we might want to just think of this as a single object in here, in the universe. Since we have a specific tuple here, right? Something consisting of 1, 2, 3, 4 ingredients. And they're ordered. This is first, this is second, and so on. So the order is important here. So if we know how to represent an ordered pair, then maybe an ordered quadruple can be seen as an ordered pair of ordered pairs in a way.
Yes.
So,
and then you can carry on this process.
Yeah. So the key idea is how to define ordered pair of sets as a set, and there is an elegant solution to this problem. Let me first maybe emphasize why it is not so trivial. So if you just want to define it as a set of two elements, then this will not work, because since the order of elements in a set doesn't matter, we will then get that AB is always equal to BA. This is something you definitely don't want, because you don't want your 0.10 on the Cartesian coordinate system to be the same as 0.01.
0.01, yeah. So position is actually matters here, and that's the problem here.
That's right. So we don't want this to be true. And moreover, we also, I mean, this is something we don't want to be true, but there are other things we want to be true. For example, we want that if two pairs are the same object, then we want their coordinates to be the same as well. And so basically the question asks how to define an ordered pair as a set so that this condition is met. Of course, the other implication.
And also the previous one also satisfied. That means in general, AB is not equal to BA. That also need to be looked after.
Well, so then they will not be equal. I mean,
if the pairs are not same, yes.
By this property, if they were equal, then A would have to be equal to B, right?
B. Right.
And then the solution, there is a solution, a well-known solution to this problem, which says that, okay, you define this as the following set. So if you take this set and you break down into its elements, it has two elements. One is itself a set having two elements, which are A and B. And the other is a set having just one element, which is A.
But is there any significance of isolating A, or I think it's equivalent if we isolate B as well?
Yes, but we have to decide on one and then stick
of them. Yes, yeah.
So this is how we basically.
They should be equivalent.
Yeah, this is how we basically isolate what is the first component of the pair. And then we can check that the rule that we wanted to hold, it would hold with this way of encoding an ordered pair. It's not so difficult to check that. So imagine it turns out that ordered pair AB equals to ordered pair CD. Then we would have this set equal.
There should be a comma in between A and B.
To this one.
Yes.
And so then there are two cases, either, I mean, because they're the same set, this element needs to be either equal to that or the other one. So there are two cases to consider, one when this one is equal to that, and the other one when it's equal to the other one.
You've got to see.
So 1 and 2. Now in the first case, we'll have our AB set equals set CD. In the second case, we will have our set AB equals set C, which then, of course, will force A to be equal to B and equal to C. You agree with that, Amartya?
Yes. Have we made any mistake? Because Partha is saying no, the intersection of A and AB is the singleton.
No, the intersection. I think there are some spelling mistakes which do not allow me to understand what's written there.
Yes.
So maybe we can come back to it afterwards. So you're happy with what I did so far?
Yeah.
These two cases. Now, in the first case, if this thing is actually equal to that, then this would leave that other element to the other element there. And so we'll have the set of A equal to the set of C, which will force A equal to C. And now because A matches with C, this will force B match with D, which is exactly what we wanted, right? We wanted A to equal C and B equal D. On the other hand, in the second case, if all A, B, C are equal to each other, so then, so remember, this is when this element matches with that one, and that should force this to match with this. So then we will further have set A equals set CD, which, because sets are equal, they will have same elements, so A will equal C equal D. So all of them will be equal to each other. And if all of them are equal to each other, then of course, in particular, the necessary pairs we wanted to be equal are still equal, right?
Yeah, they will satisfy trivially.
Yeah. So we get what we wanted. We get that by introducing definition of ordered pair this way, we can ensure that the ordered pair kind of remembers who the first component is and who the second component is. And now we can go back to here, and we can say, okay, if I knew individually what V is, what plus is, what 0 is, what multiplication is, then I know how to encode this as a set. It will be, specifically, it will be the ordered pair consisting of a few nested ordered pairs, right? So we have V plus together, put it as an ordered pair, then we order that together with 0, and then we order that together with multiplication. So we apply the ordered pair operation a few times. Huh? So this leaves us to determine how we express V plus 0 and multiplication as sets, right? And now, well, V is a set right from the start, so there's no problem there. The set of vectors is a set.
But the addition need to be looked after.
But now we, now we want to look after addition. And so what does addition do? So it's a process, but now we will turn a process into an actual set. So it's a process that assigns to each two vectors, let's say V and W, it assigns to two vectors their sum. And hence it is a function which is defined on V cross V, whose values lie in V. So we can think of plus as a function. And now the question is, how do we think of a function as a set?
As a set.
Which is, by the way, historically a significant step, because before set theory at the end of 19th century, before, in fact, Richard Dedekind's definition of a function, of an abstract function, function was really seen as, it was not seen as a set, to be short. And there is a whole history of how
sorry, Zurab, we have a question
being revised and so on. Okay, yeah.
Can you please explain why structure supersedes axiomatic formulation?
Well, in order to state axioms, we first have to describe on which object we are stating the axioms, right? So I need to describe the object first and then say what properties it should have. Like, for example, if I'm trying to describe what it means to be a human being who loves ice cream, I first should describe what a human being is, and then I should explain what it means to like ice cream. And so we first need to describe what our structure is, on which later we will put additional properties or axioms that this structure should satisfy.
Yeah,
I hope that
we have one more question. That please explain the difference between a set and a space. At this moment, we haven't defined what is a space.
So a space will be a space will be a set with some additional information. Like, we're trying to define here a vector space as a set, right? But now as a set, it's a very complicated thing. So it's actually a pair of pairs of pairs of a pair, right? So a space is a set together with structure, and we are trying to understand now how can we encode structure as a single object in the universe of sets. And for example, let's say this structure is a function. So we have here a specific type of a function of two variables, but we can think of this also as a function of one variable, where the first variable is a tuple of two other variables, right? So the general question is then how to describe a function as a set. And intuitively, what is a function? You've got two sets, and a function gives you a way of transporting elements from one set to elements of the other set in such a way that everything from your domain of the function will be transported somewhere, and that place where it gets transported to is unique. You can't have the same element being transported to two places at the same time. So we all know what a function is. The question is how to encode it as a set, because in set theory we want everything to be a set.
Yeah.
So once I have these two sets x and y.
So if we just look this intuitive terminology that we relate points on the set x with a point, and then we can get an idea how to encode it in terms of sets.
Right. So for example, if I have an element small x of capital X and I have an element small y of capital Y, the fact that x got mapped to y by the function can be written out on a piece of paper by writing an ordered pair. And if A got mapped to y as well, then we can form an ordered pair AY. So the data of such pairings is basically determines the function, right? So we can really think of a function as a data of ordered pairs. In other words, as a set of ordered pairs.
And we just now understood that ordered pairs itself is a set. So we have a set.
So we can do that, yeah. So in that way, then it becomes a subset of x cross y. A function becomes a subset of x or y. Certain pairs have been selected, not all of them. For example, if this is x and that's c, the ordered pair xc will not be included in this list. Why? Because x did not get mapped to c, it got mapped to y.
So, yeah, Zurab, I think we haven't introduced this notation of x cross y before, so maybe we should explicitly write it down. Which are the type of elements
that's a good suggestion. Thank you. So yes, so this is the notation for the set of all possible ordered pairs. So this is the set of all possible x comma y's such that x belongs to x and y belongs to y. I mean, it's a very familiar construction, of course. The real line Cartesian product with real line gives Cartesian plane, and we know that points on the Cartesian plane are seen as ordered pairs in terms of their coordinates. It's an abstraction of a very familiar construction, but now we have any two sets for which we can do that. It's still called Cartesian product of two sets. So a function can be encoded as a subset of the Cartesian product. And we can then state the requirement that it must be a function that for every x there must be unique y and so and so. But the important thing was that the structural part of the function has now been encoded as a specific set.
So basically, if we wanted to summarize this special type of collection of ordered pairs, it should satisfy two properties. One is that every element of the first component should be attached or relate with somebody from the second component, and the other one is that it should be exactly relate with one component from the second side.
Yeah, I'm writing this out. What you just said. For every x, there must exist. In fact, we could put this to conditions.
Yeah, put two together. Yes.
For every x, exactly. there exists exactly one y.
Exactly one. Yeah.
Such that the pair xy belongs to f. So this would be the definition, the axiom we want to put in order for a subset of the Cartesian product to be a function.
To be a function, right.
Okay, so we now know how to represent functions as sets, and that's basically it. Because if I go back here, after writing this down, I needed to represent each individual things as sets, and I can do that. Now V is just an abstract set. Plus is a function from V cross V to V, so it's a special case of general function. So it has been represented as a set. 0 is just an element of V, and so it's a set by default, because in set theory, element of every set is itself a set, at least in the classical set theory. And then dot, maybe we should talk a little bit about scalars being multiplied by real numbers, sorry, by vectors. So what is scalar multiplication? We take a real number R, so R is a real number, and we take a vector V, and out of this pair RV, we are producing R times V, which is still a vector V in V.
Vector.
And of course, this is just a function from R cross V to V. So it's again a function, which we know how to represent as a set. So this way, you can have any formalization of any model that describes real life situation or some abstract ideas in terms of set theory by step taking each of its ingredients. Well, first of all, if you've got an ordered list of ingredients, you can manage that as a set, because ordered pairs and their iterations are sets. And then each component of the ingredient, you analyze what kind of data it is, and then eventually you are able to, through representation of functions as sets and so on, you're able to represent each piece of data itself as a set. So everything becomes a set, and overall, an entire vector space becomes one single dot in our universe of sets.
But Zurab, I think vector space is a thing what you just mentioned, but it also satisfies certain rules which also need to be explained, that they can be also represented at least in terms of functions and hence in terms of sets.
Well, the rules are, yeah, I mean, the language which you need to write down the axioms for a vector space is just this language, right? So then there will be just rules saying, just like this one, with the function, this was some
with
rule.
scalar multiplication.
We had a rule what made a subset of the Cartesian product into an actual function, and this rule can we just copy paste it, so that the rules for a vector space can be now just copy pasted in the language that they're written, except that now we know that the language in which they're written is expressible in the set theoretic language by seeing each piece of the structure as an actual set.
No, I wanted to mean that, for example, if we take this property of the addition, which is associative, that we don't need to bother about the brackets. This property of associativity, what we generally using, denote using some notation, can also be reformulated in terms of sets, or rather more specifically in terms of functions explicitly.
Maybe I'm not sure what you mean. Let me write this out first.
Okay, for example, we know that addition is associative, that if you if you have three vectors u, v, and w, whether you first add u and v and then w is the same thing as you add v and w first and then add u. So this rule or this identity or this property or this equation, whatever we say, itself can be represented in the form of a function.
I still don't understand what you're saying. So here's the rule.
Yes.
Now this rule is a rule about the function plus.
Right.
So what do you mean when you're saying that this rule itself can be represented as
I mean, when we do this operation, first we do this operation of u and v. So we take actually actually a triple of the three elements from v. Then we do an operation of addition with first two, and then do again an operation to.
You're saying that you want to represent this rule as equality of two sets?
Yes, exactly.
Oh, okay. So yeah, we can do that. So we could. Okay, I didn't think of that. Thanks. So we could think of two sets, triples of vectors. So now this will be triple product, such that, okay, so such that this holds.
Right.
Okay. So this is now selecting those triples for which this holds, but we want it to hold for all triples. So it claims that this set is actually equal to the entire V cross V cross V. Is that what you had in mind?
No, more explicitly that we can actually avoid of this equality sign and identity or equations like that way and represent this whole identity in terms of functions only, like what you call it as a commutative diagram.
No, but that's going to category theory.
No, of course. I mean.
No, that's not needed. We don't need to do that. In set theory, we don't need to necessarily represent this axiom in a functional language. This axiom is now an axiom on an object in our universe of sets. We don't need to write it in any other way.
Because we agreed, I mean, we actually explained on the last lecture when two sets are equals, and that will be sufficient to justify this identity in terms of sets.
No, but even so, yeah, sure, yeah. We know what it means for two sets to be equal.
Yeah. Okay.
It means that, but yeah. Mm-hmm.
Yeah. Okay. Good.
Okay. So are there any questions from the audience about what we spoke of, how to represent pieces of mathematical or entire mathematical structures as sets, or maybe there are some specific structures that you would like us to look at in the next few minutes? Going to prepare my blackboard for the next discussion meanwhile.
No, so far, no new questions actually.
Okay, then I think it would be meaningful to talk about how set theory helps us understand infinity better. In fact, set theory became a theory thanks to theory of infinity.
Sorry, we have a question. We have a question. Can we construct groups using the same logic as a special case of vector space? We already have actually group within the structure of vector space, but maybe explicitly let us write it down.
Yeah. So what is a group? It's a set G. I'm going to come back to what I was saying after this. So a group consists of a set G and a binary operation defined on it. In a group, we have a few more ingredients which we could present as part of the axiomatics, but let's actually include it as part of the structure. So the identity element of the group and the inverse map. So again, it's a tuple, so we can represent a tuple as iterated pairs, right? So we can think of it this way. And now we need to describe each of the ingredients in the group. So we have G is just a set, so that's a starting point. That's just any abstract set. Then dot will be
the function.
Function, yeah, like this as before.
Like this.
One is just an element of G, and inverse is a function that maps every element to its inverse. So it's a function from G to G.
G to G. Yes.
And then the axioms. Okay, there are fewer axioms for groups, so maybe it's worth writing them out. So we have that for all x, y, z in G, x times y times z equals x times y times z, and then also for all x in G, 1 times x equals x times 1, and we furthermore have that for all x in G, x times x inverse equals 1 and equals x inverse times x. In fact, this is not the most efficient way of writing out the axioms. It's possible to remove some of the axioms and derive them from the others. And in fact, in somewhere in the 30s, there was a paper which allowed to present all of these axioms as a single axiom. And it's quite a technical result to prove that. You can present it as a single equation covering all of these. But if we don't worry about efficiency, then this is a definition of a group. And as you see, to formulate this, we just need the language provided by dot, one and inverse operation. And so that is what we call the structure. So the structure is given by dot, identity element, and the inverse operation. And so we need to make it explicit in a universe of sets what these things are. And so we make it explicit by saying that dot is a function from G cross G to G, which we already know how to represent as a set, right? It will be a subset of, so dot will be a subset of the domain Cartesian product with the codomain. So in this case, it will be domain itself is a Cartesian product, so it will be a subset of that. And -1 is a function from G to G, so it's a subset from of G cross G. So everything
Maybe it is worth it just to mention that this dot is also another name is called binary operations, just generally what we see in books or in the literature. And this single function, I mean, rather this inverse is also called unary operation.
This one is called nullary operation. Sorry, unary operation.
Unary operation, yes.
And this one is actually called nullary operation because we can think of it as a function from a singleton set.
Singleton set to
the set. So if I have a set with just one element, having a function to G amounts to selecting a specific element of G, the one where this unique element is mapped to. And so we think of the singleton as G to the power 0, and hence it's a nullary operation, where here it's G to the power 1, and here, of course, it's G squared.
Okay, we have another question, which is a little bit easier now from what is a semigroup?
Oh, a semigroup is a group without these axioms. Yeah.
Right.
Just remove these axioms and remove this part of the structure. So just leave the set G with dot, and that's together with associativity gives you a semigroup.
It's called a semigroup. And if we further drop, of course, it is not a question, but it may come that if we also drop this associativity condition, and if we have only binary operation with a set, then it's called magma.
Yes, and in the mathematical structures SATX course that started last week already, we actually discussed magmas and semigroups, and we didn't go to groups, but yeah. Okay, so I want to come back to another application of, so one application of representing functions as sets is, of course, ability to represent mathematical ideas and structures inside the universe of sets. But another application is in the study of infinity. And one can find quite interesting phenomenon there where you can discover that there can be two sets that seem to be of different size, but actually it's not so. And here is the first example. If we take the set of natural numbers, which is numbers 0, 1, 2, 3, and so on. And if we want to represent these as sets, we already discussed last time how we could do this. We could do this recursively by representing every number as a set of previous numbers, where 0 will be the empty set, and then we'll build up all the numbers from there. And then we could take the set of integers, which is the set of these numbers along with negative numbers, and we can actually define what negative numbers are in terms of ordered pairs. We can think of number -n to be ordered pair of some symbol, which we call minus, and this could just be the empty set as well, comma n. It's a symbol seen as a set, so you just pick any set that you like, you put it here, and then you form the ordered pair, and that's how we can formalize -n as a set. if n is formalized this way. You can no longer base it on the idea of amount of elements, because you can't really have negative amount of elements in a set, although there is some research which tries to explore set theory with negative amounts of elements. And then one asks this question, which is more? Are there positive natural numbers more, or the integers?
So what does it mean by more?
Well, I mean, if you have two quantities, you want to compare which is more, right? I mean, like, for example, if you had two sets, let's say one set has 3 elements in it, and the other one has 4 elements in it, then you wouldn't ask me what is more, right?
Right.
By the way, a very curious phenomenon is that you can compare the sizes even not without knowing counting. You just pair things up, so you basically establish what is called a one-to-one correspondence, or an injective function. I mean, one-to-one mapping. So you pair each element of one set with another one. So you consider a function. Let's say this is two sets, x and y. You consider a function from x to y. And remember that function has already been represented as a set, so it's a subset of the Cartesian product. You consider a function from x to y with the property that for any x1 and x2 in x, if x1 is not the same as x2, then f of x1 is not the same as f of x2. So this allows you to say that two things cannot map to the same object. They always must separate to separate objects. And if you can do that, right, it means that whatever you have here, you've got counterparts there. And if you have something left over, then surely the other set was more than the previous one.
More elements, right. But
okay,
based on the fact that what we described in the previous lecture, that we talked about subset. So definitely we can say n is a subset of Z, because all those elements are in Z.
Yeah, definitely n is a subset of Z, and being a subset of Z, we can map every number to itself in the other set.
Right.
And this way we can say that there is at least as many elements in Z as there are in n, but possibly more. And in fact, we see that there is some left over, so
yes,
there must be more. Huh? Now, if it turns out that we can also do backwards, we can also have a backwards correspondence, then Z, n and Z will have the same amount of elements. But if we can't,
sorry, we have a question. Can you please show how the definition of minus as the of minus n plus n 0, if you can choose any set to represent this?
Yeah, I saw that question, Amartya. I think
okay.
Let's finish this topic first, and then
then we can
return to that question. Yeah.
Sure.
So we can see from this picture that, I mean, also intuitively, that there definitely are at least as many positive integers as there are all of integers. But what about the other way around? If the amount were the same, then it should be possible to establish a mapping so that after that nothing is left over, right? There is exact match.
Yes.
And it turns out there is such a mapping between n and z. And I guess many members of the audience already are familiar with this quite well. So, but maybe not everyone. So let me make that explicit. So these are on the left side we have the set of natural numbers. On the right side we have the set of integers. So I'm going to add the negative numbers as well. So it goes on in both directions now. And now I'm going to establish a one-to-one mapping which does not leave anything unmapped to on the right side. So let's map 0 to 0.
We want what we explained in the terminology, it should be an injection, as well as there shouldn't be any additional elements left on the right-hand side, which is not associated with anybody on the left-hand side.
Right. So since you mentioned the term injection, let's maybe write this down here. So
Right, yeah.
another word for one-to-one mapping is that F is an injection, as you said.
Yeah, or into, because both of these terminologies are
Yeah, but I
used.
think having too many terminologies will be confusing. So let's stick with one.
Yeah.
So we can map 0 to 0, and then we can map 1 to -1, and then we can map 2 to 1, and then we can map 3 to -2, and then we can map 4 to 2, and we can map 5 to -3, and then we can map 6 to 3, and it goes on like this, and we will never run out on this side. And you see, we're expanding the range of what things are being made use of after being mapped to, right?
Right.
And eventually it will cover the entire integers. So there will be a one-to-one corresponding.
There is a pattern here, how we're doing this map alternatively, starting from 0.
So you want me to write down the explicit formula?
Yeah, maybe that will be easier to understand, or rather for checking purpose for the participants who wanted to really check it.
All the even numbers are being mapped to the n. So 2n, numbers of the form 2n are being mapped to n, and numbers of the form 2n plus 1 are being mapped to, is it minus, let me figure this out, minus n minus 1? No.
No, because 5 should go to.
Let's see. So one goes
-3.
to -1, right?
Right.
So if I put 1 here, okay, so it's just minus n, I think. Then 3 goes to.
Not really. Yes. No, not really. Because 5 is going to -3.
Yeah, so to get 1, we need n to be 0. So that's.
Yes.
Right, so we need to have minus n minus 1. Does that work?
Yes, 2 minus 2, yes, I think so. Because 3 will go to -1, yeah.
And also works for 5. Yeah, I think this will work.
Yeah. No, it's fine. Yeah.
So it turns out that the size of a set is usually written like this. It turns out that the size of the set of natural numbers is the same as the size of the set of integers. And now one wonders whether that size is still the same as the size of other number systems. And it turns out it's still the same as the size of the rational numbers, but it's strictly not the same as the size of real numbers, which turns out to have the same size as the size of the power set of the set of natural numbers. And remember what power set of a set is. It's the set of all subsets. So let's just recall what this thing was. We did some computations with power set last time. So it's the set of all S's of all sets which are subsets of the set of natural numbers. And in general, you will never, no matter what set you have, this size of that will never be the same as the size of its power set. So this is the theory of infinite sets as developed by Georg Cantor, which turned set theory from language into a theory. So you can actually get new insights about infinity by formalizing things in the language of sets. And one of the things that Georg Cantor wanted to figure out is whether there is a set that's strictly in between natural numbers and real numbers in terms of its size. And this thing is called Continuum Hypothesis. And he couldn't figure this out. And then later on, after he wasn't alive anymore, it was possible to understand what's happening here. And the clarification of the story is that it turns out that in some universes of sets, such X does not exist. There's nothing in between natural numbers and real numbers in terms of size. But you can also build some other universes of sets where such X may exist. And the technique for building such universes is called method of forcing. That was introduced by someone called Cohen, who also got, I think, the Fields Medal for.
Fields Medal, yeah. PM Cohen. Yeah.
So,
by the way, by universe we wanted to mean a set of axioms.
No, well, yeah. So I mean this thing. So I mean a world of sets, which we talked about last time. So we can have many different universes of sets, and how to enlarge a given universe of sets so that it solves some set theoretic questions. That was the idea of Cohen, which, by the way, was a bit inspired by discussions with Gödel, who was already also thinking about these questions. But now I'm not going to go into history too much. It's possible to read up on all of this on the internet as well. Okay, so somehow this idea of precise language, of turning discussion of sets, which seems like a childish concept, into mathematical discussion, it allowed one to formalize the idea of infinity and bring in the idea of infinities having different sizes. And research in set theory is very much about establishing theorems about infinite sets. So set theory has this aspect that you can research in set theory by studying infinities, but it also has the aspect of a language that you can use this set theory as a language for formalizing all of your mathematics into one common framework. So no matter what you're doing in mathematics or its applications, you can always pretend or actually explicitly work in a context which is universal for all different areas of mathematics, which is the thing that's nice about this theory in terms of its applications, of course. Okay, now coming back to the question we had, right?
Yes, we have this last question.
Can you please
to describe,
show that
yeah,
minus has v of the property of minus n plus n equals 0 if you can choose any set to represent minus. So we are not going to show that it has this property. We are rather going to define addition of numbers in such a way that this property is validated. So we are not going to prove that this property is true. We are going to define, because we haven't defined addition yet. So we have here the set of natural numbers, right? And we are now defining minus n as this, but we haven't defined addition yet. We still need to define addition.
In this new set.
Yeah, we have to define addition as a function from n cross n to n. And so we will define addition in such, sorry, z cross n, z cross z to z, right? We now want that. And we will define addition in such a way, yeah, that by definition this will hold.
Yeah.
Okay, great. So the one who asked the question was satisfied with the answer.
Yes, yes. So, right, so maybe we stop here and check for others. Any questions, remarks?
So while we wait for any possible questions, let me just summarize the two main points from today's lecture. One is that set theory can be used to formalize all mathematical structures,
concepts,
ideas, concepts, therefore, and so on,
yeah,
in one common universal language. And the second point is that set theory can be used to study infinity.
Infinite sets.
And such a study leads to insights which previously were not known. In fact, this thing that I described here, the fact that the size of n is the same as the size of z, this was one of Cantor's, if I'm not mistaken, this was one of Cantor's original results, first results in set theory. Okay. I think we are ready to pass on to
Francesca. Yeah.
Francesca, yes.
No, I was just checking whether there are some raised hands. Or
Yeah. There are 3 more questions possibly.
But I don't see any at the moment. Yeah.
There are a few questions that have arrived. Huh?
Yes.
In the Q&A. Yes. Okay, but most of them you have already resolved.
Z times Z and Q has the same size. That's one question.
Yeah.
Yes, the answer is yes.
Yes, the answer is yes.
Yeah, I could explain, but I could actually explain. It's not so long. So once we agree that Z is the same size as n, after that the explanation is not difficult. So we could think of so that I'm going to slightly change the question. After knowing that n has the same size as z, the question now becomes, why is this true, that n has the same size as n cross n?
N cross n.
And the way you argue about this is that you write out your order. This is Cantor's argument. You write out your ordered pairs in a matrix, in an infinite matrix. And then you establish one-to-one correspondence with natural numbers. Okay, I forgot about the 0, 0, but let's now start with 1. For the time's sake, I don't want to make corrections. And you establish one-to-one correspondence by mapping this there, and then all these consecutive numbers mapping along the zigzag. So like this. So 1 maps there, 2 maps here, 3 maps here, 4 maps there, 5 maps there, and so on. And each diagonal in the zigzag is finite, so we will be able to get one-to-one correspondence between the set of natural numbers and the set of entries of this infinite matrix. So this is called.
And the same argument will work for his question as well.
Yeah, because this is the same as Z, and that's the same as Q, and so then
Right.
the answer to this question follows.
One more question is there. In brief, what are the mathematical implications of continuum hypothesis?
Well, some technical implications in set theory, nothing too significant that I know of. So it's more an interest in the study of infinity rather than having some specific applications outside that study. But it was fascinating that it was difficult to establish, and when Cantor dreamed to establish something like this, but he couldn't, and then it was fascinating that it was possible to resolve the problem.
As far as I remember, of course, I am not quite well known about these areas. Continuum hypothesis has some role-playing descriptive set theory, but yeah, as you mentioned, it's more the structural aspects of the foundational things which plays the role as applications of.
So Partha suggested something now which we could leave as a fascinating exercise for whoever is listening to this. In fact, I've been using this exercise to identify students who are really passionate about mathematics. If you have 2 sets, x and y, and you can find an injective function in both directions, then prove that it's possible that the 2 sets do actually have the same size. In other words, that there is a one-to-one correspondence between x and y. So if these are injective, both of them prove that this holds. This is called Cantor-Schroeder-Bernstein result, and the proof of this is very is a fascinating process to prove this. And in my experience, once you prove this, you become extremely passionate in mathematics. It has been tested on a number of students who are now mathematicians. So
And
it's not just.
We should do it next week then. Yeah.
Yeah.
Excellent. Then I still don't see anyone raising the hand. So I assume that in the course of the lectures, we address all the issues and comments raised in the Q&A. And since we reached 4 o'clock, it is then my pleasant duty to thank very much Amartya and Zurab for another really great and inspirational lecture that I hope all the participants enjoy. Yeah. And I'm looking forward to next week.
Thank you so much, Francesco.
Rounding up this very nice introduction to set theory with lots of historical comments that are really very nice. Thank you very much to both of you. Thank you. And I'm sure I can thank you on behalf of all the participants. Yep. So then thank you very much, everyone. Have a good rest of the day. And some of you need to keep warm, I can see. And hopefully the summer comes sooner rather than later. Yeah. Thank you very much. Thank you. Have a good afternoon.
Thank you. Thank you, everybody. Thank you. Goodbye.
Thank you, everyone. Bye-bye.
Bye.